All right, so we are ranking potential energy of capacitors. And right away, if I'm going to do this, I better know that U sub C, the potential energy stored in a capacitor, is 1/2 Q delta V. I better also be able to say 1/2 C delta V squared. And I better be able to say Q squared over 2C. Don't ask me why that one's written like that. It just normally is, where the others have a 1/2 in front of it. Otherwise, yeah, these are all just like they come from that idea that if you made a graph of the voltage versus the charge stored on a capacitor, the area beneath here ends up giving you the potential energy, like because a volt is a joule per coulomb and Q is measured in coulombs. So that's where that 1/2 Q delta V comes from. And then all these are just ways to manipulate that with Q over delta V equals C. So looking at this first one, looks like they all have the same Q, but they have different C's. That leads me to say, hey, Q squared over 2C equals U sub C is the best way to justify it. And therefore, since they all have the same charge, same pluses, same minuses right there, the one with the most capacitance will actually have the least potential energy. So they rank like this. If I said like U sub this one and U sub this one and U sub this one. Like this one has the most and this one has the least. Turns out one way to justify that is if I had them, like if I reconnected it like that, how quickly would they jump across here? And here, these charges would like neutralize really quickly and they'd move real fast and let off a whole lot of energy as they're moving real fast because the air doesn't hold on to them as well as the water because they're increasing in dielectric constant. Water is a bigger dielectric constant than mica, than Teflon, and then air. So the bigger the C, the smaller the U. That's my justification here. Here, I see that they now have different Q's, but the same C's. Well, and I'm still going to use Q squared over 2C equals U sub C. But in this case, it's like Q is the thing that's changing, and C is our constant. But here, the more charge, the more potential energy. So this one's bigger and bigger and bigger than that one. Down here, I see that they all have the same Q's, but they have different amounts of volts. They also have different capacitance, so you could use a bunch here. But I'll use U sub C equals 1/2 Q delta V, realizing that the more delta V they have, the more potential energy the capacitor has with the same charge. So therefore, this one has more potential energy than this one. Awesome. And this is all just like when there's lots of different ways to represent something, just find some constants, find some things that are changing. And here, it looks like they have the same charge, but different capacitances. So I'm going to jump to this one again. Q squared over 2C equals U sub C. I've used that one a lot, but that's just by chance. This is the only one where I had any information about volts, so it was the only option I had for doing either 1/2 QV or 1/2 C delta V squared. No, that'd be a terrible decision because both C and delta V are changing. So here, all right, same charge but different capacitance. The one with the most capacitance will have the least potential energy. So right here, this is the best capacitor, so that's going to have the least U sub C. And then the worst capacitor is this one, and this will have the most potential energy stored in there. And that, I also need this idea, recognizing what makes a good capacitor and not. Take a look, make sure you can do the same, and you can rank all of these and compare what makes a good capacitor and what makes it have a lot of potential energy on it.